Hello everyone, welcome to my channel. If you are new to my channel, please subscribe to my YouTube channel, so you can join our tech family. If it is informative to you, please like our video, share it with your friends so they can get help with these video, and don't forget to press all notification bell icon so you get regular update and don't miss any single video.
Hello, this is IT. Have you tried turning it off and on again?
No, I'm just having a problem with the server. I can't even ping it.
Yeah, that sounds like a layer 3 problem. I don't do those. Bye.
Aside from being the worst support call in history, what else is interesting about this? The support officer mentioned layers. He is talking about a layer of the OSI model. But what does this mean? And why is it important to us? That's what we're here to discuss in this video. All devices on the network have network hardware and software. They need to speak a common language. That is, one host needs to communicate in a way that another host can understand. These languages are called protocols, which we discussed a little in the last two videos. But there isn't just one protocol that makes the magic happen. Several protocols need to work together to get the job done. But trying to track how they all interact can get complicated. And that's why we have network models. They help us to understand how everything fits together. We're going to go off on a tangent for a little while and use an analogy to describe the layered model. Think about sending a letter or a package. There's a lot of parts to this process, some of which you don't even see. We're going to use this process to explain how models work. To start with, you write a letter. You then take that letter and put it in an envelope. You write the sender address on the back and the receiver's address on the front. You put a stamp on the letter. Now you take it to the local post office. The staff there will work out where it needs to go and put it on the right truck. It then gets delivered to the destination post office. A postman takes the letter and delivers it to your friend's house. What we've done here is we've built a model. This describes how each of these parts interact, but the details underneath may change. For example, maybe we're not writing a letter, maybe we're sending a package. The address may be local or it may be international. This of course changes the number of stamps we'll need. When we're ready to send the letter, we could take it to the post office or drop it at a post box. Maybe a private courier will come and pick it up, or perhaps a bike messenger will be involved. It can then be taken to its destination by truck, plane, ship, or some other combination of transport. And finally, it may be delivered to a house, a business, or to a PO box. The important part here is that we can take a model and we can use it to understand the overall process. We don't need to know any specific details to start with, but the model can help us to understand them in the end. The OSI model can help us to understand the network. It breaks the network up into 7 layers. These layers are physical, data link, network, transport, session, presentation, and application. And if that's a bit tricky to remember, think of this mnemonic. Please do not throw sausage pizza away. I know it's a bit silly, but it helps us to remember the layers and their order. Notice that these are all generic layers. There's no Ethernet layer or email layer. The OSI model is not about specific technologies, but rather how they fit into the network stack. Imagine that we have an application on one host that needs to send data to an application on another host. Let's now see how this data moves through the OSI model. The data, as the application sees it, starts at the application layer. This is where network APIs and apps that access the network live. For example, this includes FTP and web browsing. The data needs to be in a format that can be easily understood. That's what the presentation layer is for. Anything related to data formats lives here, such as image and video files. The session layer tracks application processes. This includes remote procedure calls and service requests. Think of this layer as building a session between a local application and a remote one. You can probably see that the session, presentation, and application layers work with very large pieces of information. But that doesn't work well for lower layers. For instance, what if the data you're transferring is very large? Maybe this doesn't seem like a problem on the surface, but what happens if you get right to the end of the transfer and the connection is interrupted? You would have to start the whole transfer again. Also, any other application that wants to use the network would have to wait until this transfer is complete. Fortunately, there's a way around this. When the data reaches the transport layer, it is broken into manageable chunks. Now, if there's a problem with the data, only one chunk of data needs to be resent, not the entire file. Also, apps can take turns at sending chunks of data, rather than one app hogging the host's resources. This is called multiplexing. Sometimes we need to add more information. Adding the destination address is an example of this. Any information we add to the front of our data is called a header. Any information we add to the back is called a trailer. As you can see, each piece of data gets bigger and bigger as it moves through the network stack. Eventually, the data reaches the physical layer, where it is transmitted over cable or wireless to a remote host. The remote hosts receive the data at the physical layer. The process is then reversed. The data flows back up through the layers. Each layer does its job, removing headers and trailers and converting the data until it is in a form that the application can understand. Can you see here that each layer will only communicate with the layer above and the layer below? Each layer has its own job to do and doesn't get involved with other layers, other than to pass and receive data. You can probably see how this makes it easy to combine different protocols to achieve different tasks. Now, I'm going to pose you a scenario. You're working in the network team and users are complaining that a new high bandwidth application is causing the network to slow down. Which layer do you think needs to be addressed? Well, I'm going to leave that for you to think about. We'll now take a closer look at what each layer does. Afterward, we'll run through an example of how this might work. Developers and application specialists spend a lot of time in the upper layers. This starts with the application layer. This is not strictly the application itself, but rather it's how the application accesses the network. Some examples of this include web browsing, accessing emails, and transferring files. It also includes management sessions like SSH, Telnet, and RDP. The application may contain a lot of data. This data may not always make sense to the rest of the network, so the presentation layer helps by converting it if needed. This conversion may also include services like encryption and compression. File formats also live here, including images and video files. An application may need to talk to several other endpoints, so it is important to track where these conversations are occurring. Each of these conversations is called a session. It's not surprising that this is handled at the session layer. Traffic you would see here includes requests to remote services. You may have heard of Session Control Protocol, or SCP. It lives at this layer too. The transport layer is used to transport traffic between processes onto endpoints. You've probably heard of TCP and UDP. These are the most common protocols used at this layer. Earlier we were talking about how data, if large enough, needs to be taken and broken into manageable blocks. That's part of what this layer does. Generally, we call this block of data a segment. Technically, if you're using TCP, each block is called a segment, but if you're using UDP, each block is called a datagram. So now we have many blocks of data, probably going to different hosts for different applications. So how can we track what goes where? The answer is through port numbers. Each flow of data has a port number associated with the source and destination host. These values are added as part of a header to each block of data. This may be easier through an example. A web server will use port 80 to listen for web traffic. A workstation will send a request to the web server with port 80 in the header. It will also select a source port and send that along as well. The web server will send a response back to the workstation using its port as the destination. But to send information from one host to another, we need some form of addressing. In addition to that, we need a way to route through the network. That's what the network layer is for. One of the common protocols we see here is the Internet Protocol, or IP. This layer adds yet another header. In the case of IP, this includes the source and destination addresses. Once this is done, the block of data is now called a packet. Now we need to think about getting data from one device to another. This is where the data link layer comes in. Notice that the goal is to get data from one device to another. This layer does not try to get data to the end device. That's the responsibility of layers 3 and 4. Part of this includes establishing a logical link between the devices on the same network segment. We need to have a logical link as devices probably aren't directly connected. They're usually connected with a shared medium like a switch or over Wi-Fi. A well-known protocol here is Ethernet, which uses MAC addresses. Yet another header is added, which in the case of Ethernet includes the source and destination MACs. A trailer may also be added with error correction information. Once the header and trailer are added, this block is now called a frame. As data moves across the network, it will likely pass through one or more routers. As each of these routers are a separate device, the destination layer 2 addresses will change with each hop, but the destination layer 3 address will remain the same. The data link layer is special as it contains two sublayers. The logical link control sublayer is responsible for translating between the network layer and the data link layer. The media access control sublayer is the part that's responsible for adding headers and trailers to the packet, creating the frame. It's also responsible for error correction. And finally, the physical layer. This concerns itself with the physical components of the network. This includes radio frequencies and channels, pulsing light, pins, electrical signals, and standards of copper cabling. Further, this means that the physical layer is responsible for encoding information in a way that can be understood. For example, what electrical signals represent a 1 or a 0? Or what if wireless is used? If you want to dig deeper into this topic, the CCENT guide is quite good. Also, I have more information on my website, and I'll include a link to both of those in the description. So, is this making sense to you? Tell me, which layers do each of these items live in? I'll put the answers on the website, of course. And while we're at it, pause the video and see if you can match the layer with the description. How would you like to see an example of how this works? Well, protocols these days do not fit the OSI model exactly. Remember, it's just a reference model to help us. But still, let's try looking at a client sending a request to a web server for a web page. On the client side, the web browser is the application. A user opens their web browser and types in a URL. The web browser uses a protocol called HTTP to prepare the request. This request is the data that needs to be sent to the server. HTTP doesn't simply fit into one layer. If you're sitting an exam, HTTP is considered an application layer protocol. However, practically it spans a few layers. So, we'll say that it's an upper layers protocol. It creates the request that we want to send, and it makes sure any special characters we're sending are properly encoded. HTTP doesn't really manage a session in the upper layers. That's managed by the transport layer. At this layer, a protocol called TCP is used. One of the first things that TCP will do is break the data into segments. We're only talking about a small request here, so TCP shouldn't really need to break up anything in our particular case. It does still need to create the session we were just talking about. The first part of this is assigning port numbers. HTTP usually uses port 80 on the server side. This is the destination port. The client simply generates a random port number and uses this as the source port. These port numbers are added to the data in the form of a header. TCP then stores all this information in memory. This is how it keeps track of the session and knows which application is waiting for the response. Now the network will add addressing information. In our case, we're using IP addressing. It firstly needs to know where to send the request, which it can get from the URL. This becomes the destination address. It also needs the address of the client, so the web server will know who to respond to. This is the source address. These addresses are added to the segment as a header. They are also stored in memory along with port numbers to track the session. But you've probably noticed that the client and server are not directly connected. They're on different networks which are joined by a router. So the packet can't be sent straight to the server. It needs to be sent to the router first. In our data link layer, we have the Ethernet protocol. This creates a logical session with the router. Ethernet will create a header for the packet containing the router's MAC address as the destination and the client's MAC address as the source. Notice that we don't need any MAC addresses for the switch. A simple switch operates at layer 2. It's only there to forward frames to the correct device. Ethernet also includes a small piece of error correction information called a CRC at the end of the packet. And finally, it's time to convert the frame into bits and put them on the wire to be transmitted. Our data moves through the switches without being altered and arrives at the router. The router then takes out the source and destination MAC addresses. It now puts the server's MAC as the destination and its own MAC as the source and sends the packet on. It also generates new error checking information. The server's NIC receives the electrical signals from the cable. At the data link layer, the server will check that there are no errors with the frame by checking the trailer. If all is good, it strips off the layer 2 header and trailer and inspects the IP address information at layer 3. It will check that this packet was indeed meant for itself, and it will store the source and destination IP addresses in memory so it can reply later. It now strips the layer 3 header off and looks at the source and destination ports. It will store these ports in memory along with the IP addresses. In this way, it has also established a session with the client. It sees that the destination port was port 80, and it knows that it has web server software listening on port 80. The data is then given to the correct application, and HTTP will take it from there. The server will of course want to send a response. It will go through the same process to send that over to the client.
We hope you enjoyed the video and found value in the content. We value your feedback. If you have any questions or suggestions, feel free to post them in the comments section or contact us directly via our social platforms. Thanks for watching.